So I'm going to apologize ahead of time. I don't know how long this video is going to be, but it's not going to be a short 5 to 10 minute video. The intent is that this will now serve as your 25-point pre-lab. So there won't be any separate pre-lab. Your pre-lab questions are going to be sort of embedded within this video, but I want you guys to be able to come into lab on Thursday ready to go, since we're only going to have 90 minutes to essentially get through 3 activities that I normally do in a three-hour period. I want to make sure that whatever I would have talked about before we did that experiment, I talk to you about it now so that you're kind of ready to come in, get your data, and then get out. All right, so this is actually normally a lab I do a little bit later in the semester. We do sort of some more preparatory work first, but I want to make sure that we got in and got our wet lab experiments done as soon as possible here. So this is just what we call a BBT lab, a basic biochemistry techniques lab. So we're going to have several boot camp labs. 2 of them are not wet labs, so I'm going to kind of do things a little bit out of order and flip those till a little bit later here. So today's experiments are going to be pretty much threefold. I'm going to split them into 3 30-minute blocks. We're going to have stations set up for you guys in lab, and I'll talk to you about that in a minute. We're going to have a station for pipetting, a station for putting some materials together to use for spectroscopy, and then a station to allow you to think about using a pH meter. Now, a lot of what will be happening in tomorrow's lab will be me demonstrating things for you, but I do want you guys to have the opportunity to be able to see how this stuff happens in real life. As we work through this lab, I want you to think about 2 important things. I want you to think about accuracy, and I want you to think about precision. I'm going to go ahead and silence notifications there. All right, so this is actually from a handout that you'd normally get at the end of the semester to help you prepare for the final exam. I'm not yet certain how or if we will do the final exam. It's normally like a practical as well as a written portion. We'll have to see how everything sort of shakes out this semester. But these learning objectives are still really important for what I want you to take from this lab. So again, terms and information to know, again, limits and how to use pipetters. So if you've used pipetters before, that's awesome. We want to make sure that we understand for the 3 pipetters that we have, what are the limits that we have with those, and make sure that everybody's using them correctly. For a spectrophotometer, again, thinking about the limits for what's reasonable in terms of experimental data to obtain from a spectrophotometer. How to use our actual spectrophotometer, again, I will be doing that for you tomorrow. And then importantly, how and when to think about using Beer's Law. And then for the pH meter, again, I will demonstrate how to use the pH meter, but understanding how to calibrate it, how to get it ready, and again, limits for the pH meter and how to use it. Conceptually, we are going to be using balances. So we'll talk about when we weigh things, what's more important, that we measure this amount exactly, know exactly the amount we measure, or are neither really important? Being able to use that skill in lab is going to be essential to you being timely and efficient in lab. Again, this thread of accuracy and precision. So again, accuracy meaning how close you are to a true value, and precision meaning how close your actual values are to each other. So we're going to talk about those 2 concepts in what equates to a fairly simple lab to teach us how to use some equipment, and then again thinking about these concepts of accuracy and precision. So from a skill standpoint, quite a few things that we're going to practice in lab. The first thing is how to make a solution. This is one of the things you're going to have at the end of the semester in the lab practicum. So I'm going to ask you to make a solution, right? So you have to know which laboratory glassware to kind of grab and pull from. So just a quick overview for this. We range from beakers to graduated cylinders to volumetric flasks to pipetters. And that order is really the order that we have of kind of the accuracy of them. Beakers are not very accurate in terms of what they measure. Graduated cylinders are better. Volumetric flasks are even better, but we only have 1 volume we can measure in a volumetric flask. And then obviously pipetters are really great because we can have lots of different measurements that we feel like we can measure accurately. So we'll talk about different pipetting techniques. You'll do an experiment today where you'll have 3 different pipetting techniques that you'll try, and you will actually use your data to determine which is the most accurate and which is the most precise. We're going to make a solution then that you will analyze by spectroscopy. So again, using that spectrophotometer. So we're going to do two things with the spectrophotometer. First thing that we're going to do is obtain a wavelength scan. We'll talk about these details in just a minute. But a wavelength scan is going to look at the absorbance as a function of a bunch of wavelengths. That's going to allow us to determine what's the best wavelength to actually do the rest of our measurements at. So that's a wavelength scan. And then we'll also do a fixed wavelength measurement. Once we know what that best wavelength is to use, then we'll actually use that wavelength in a much quicker way, gather some additional data. We'll also generate a solution that will measure the pH of. You guys will actually calculate what the predicted pH should be, determine what the actual pH is, and then hypothesize if it's not right, why that is the case. So there's an additional opportunity to work on doing some buffer calculations, so that'll be part of that pH station. So those are the overall learning objectives that we're going to have for this lab. From a practical standpoint, you guys are going to walk in. At most, we're going to have 5 students. So there'll either be 4 or 5 students in lab. You'll each have your own bench. I will probably be set up someplace up front here. I might spend some time kind of in the back area sort of observing. You guys will each have your own area. We're not going to be sharing equipment. And so you guys will have most of the equipment that we'll be using ready for you at your designated area. So you'll have a set of pipettes at your station. You each will have a balance at your station. And then I will be having and using the spectrophotometer as well as the pH meter up in my area. So these are normally pieces of equipment I would teach you how to use on your own, but in kind of the situation that we have right now, it's more important that you just see how to use it, not that you actually use it yourself. So our first station is going to be on pipetting. And many of you maybe have used pipetters in another class, but we're going to make sure that you are comfortable with using the pipetters that we're going to have available. So again, everybody is going to have these 3 pipetters at their workstation. So the 3 pipetters that we have are what we call a P20, a P200, and a P1000. There are 3 different colors, and those colors correspond to color-coded boxes that have the correct kind of tip in them. So one of the skills that I want to make sure that you are comfortable with is knowing the limits that we have for what we can measure. So again, P20 is pretty much 2 to 20 microliters. P200 is 20 to 200 microliters. And then P1000 is 100 to 1,000 microliters. So obviously anything greater than 200, you have to jump up to a P1000. Anything in the 100 to 200 range, you actually could use either one of these, but you're probably going to get more accuracy with your P200. So again, knowing upper and lower limits of pipetters is important. Also knowing how to read one of the pipetters. Okay, so here is again the P200, the P20. One of the things we'll see here is this pipetter and this one have red digits. You can think of those red digits representing where decimal points would be. So for example, if we're reading this would be 5.64 microliters. So again, there's a decimal point that's right there. So 5, and we definitely know the 6, and we're guessing at the 4 that we have there. For the P100 or the P200, these are all black numbers, so there's no decimal point that we're going to have there in the numbers that we read. Now, it's not to say that there's not a decimal point. We're going to estimate the number that we see for that. So we're certain of 1, 0, and then we're less than 5 here, so this is going to be 104.8. And then again, for the P1000, this is going to be one where this really is the decimal point between, this would be going between a 0 and a 1 to be 1 milliliter. This is a classic pipette that students can kind of make some mistakes on. If this is a 1 and this is like a 100, if that's what we read here, that's really 1 milliliter. It's going to be 1.00 milliliters. So there's a decimal point right here. So this is 0.35, and then we're estimating here 4. So 0.354 milliliters is 354 microliters. So making sure that you're good at measuring a pipetter is really important. Normally I'd go through sort of a tutorial sort of online with how to use pipetters. So I'm going to kind of try to walk you through how we do this here. I don't have a pipetter at home. I wish I did here, but there's a dial that's on the top. Okay, so this really represents a dial that's on the top. You can think of this as the parking brake, when we turn it, and then there's a little lock there. So it's a little bit hard to see here, but you can see the edges of a lock that's there. You can think about that lock kind of being your parking brake. So when the parking brake is off, this dial will rotate easily, and we can easily change the numbers. So just like you don't want to drive your car if the parking brake is on, don't turn the pipetter unless the parking brake is off. So in this case, once you set a value that you want to measure, you're going to lock that parking brake, if you will, because as your thumb pumps up and down on that wheel, you want to make sure that you don't accidentally change that value that's there. Okay, so that's the important thing with that dial and that lock with how we're going to use these. Another thing with how you use your pipetter. As you use it the first time, you'll notice as you push this button up and down, you'll notice that there's a soft stop as you go down, and then you can push all the way through to a hard stop. Okay, so there's like a first stop and then a little bit more to go all the way. When you are going to be using these, in general, we'll talk about a few specific times later on where you maybe want to do something different. You want to push down to the first stop, put your pipetter in the liquid, slowly release your thumb to draw up liquid, and then take your pipetter out. So I'll demonstrate just real briefly when we're in class kind of proper pipetting technique. But I talk about doing things at eye level, right? I like to be able to see where my liquid level is. We also want to think about playing the game operation. We want to make sure that we don't contaminate the shaft of that pipette or as minimally as possible. So we kind of want to make sure as we're going in, we're cognizant of that. You can also use pipetters for mixing. So if you again want to take and mix some solutions together, you'll often see people using a pipetter to mix. Pipetting should be a fairly silent activity though. You never want to be releasing that spring-loaded plunger very quickly. Okay. Again, thinking about contamination, think about the game of operation. We kind of want to make sure that we're not contaminating these pipettes, or if we do, that we wipe them off before we go into another sort of container to draw something else up. I know these were questions that maybe came up when you did burettes in general chemistry, kind of thinking about what do I do with this drop of liquid? Okay, so something to highlight here, if liquid is getting sucked back up inside your pipetter, that's usually an indication that the seals are a little bit leaky. That's definitely something to let me know about. If you have a drop that's on the outside, so if you pull up from your solution and you see that there's liquid on the outside of the pipetter, you don't want to transfer that. The only liquid that you've counted per se is the liquid that's inside the pipette tip. So if that's on the outside, you might want to just sort of wipe that on the container as you pull it out to kind of put that drop back in the container because you didn't measure that. Again, what should you do if there's liquid still on the inside? That is liquid that you measured and counted. So we want to make sure that we quantitatively transfer that. That's where this last stop is going to come through. So when you deliver liquid, you push down on the plunger to let it come out, and then you can go all the way through to kind of have a little bit more air that comes out to push all of the liquid out. Okay, so I will re-demonstrate this when we're in class, but again, just highlighting there's going to be 2 stops. When you're drawing up liquid, only go down to the first stop and then pull up. When you're transferring liquid, you can go all the way through to kind of give a final push for that quantitative transfer. All right, so that's a little bit of nuts and bolts on using pipetters. I want to talk about 3 different methods of pipetting that you guys are going to determine the accuracy and precision of. The first is a shooting method, and this basically where you're going to dispense liquids by shooting it out without touching the tip to anything. Okay, so I'll demonstrate that before you guys do it, but each of these methods has some pros and cons. The first method here, this shooting method, is going to be really helpful if you want to be green. I'm going to talk about being green versus being clean. Green meaning we're being environmentally conscious. We're not throwing away more plastic than we need to. And then clean means, you know what? I have to make sure that I don't cross-contaminate my samples. So a pro of the shooting method is that it really limits contamination because I haven't touched this pipetter to anything else. So I can go back into my original container and then kind of have it come back out. So again, that's going to be a nice a green method because I'll be able to reuse that pipette tip. The cons is, in general, you guys are going to get some data to confirm or refute this, it tends to be the least accurate method of delivery, okay? But again, there might be a time where you don't need to be super accurate. You're just delivering some buffer solution to a variety of samples, so it might be easy to just kind of go along with this shooting method. Touching method, okay? Now we're going to dispense liquids by touching the tip to the side of whatever you're transferring it into, whether it's an Eppendorf tube. You guys are going to use a little weigh boat. Again, the pro of this is it tends to limit contamination. So it tends to be a green method because we are not using that, or we are using that same pipette tip. But again, a con of this is we tend to have incomplete transfer or mixing to a solution. So if we have a small volume that we're sort of adding to another vessel and it kind of gets stuck on the wall, we're thinking that we're transferring all of that in there, but we're not necessarily getting it there. Okay, so that's sort of a con of it. So ways that we can get around that, we'll talk about those as they come up sort of with each experiment that we do and whether we want to use a shooting, touching, or the immersion method. The immersion method is going to be where we dispense liquids by literally immersing the tip that contains the liquid inside the liquid in the transfer vessel that we have. So clearly this is if you've already put some liquid in there. Pro of that is we're pretty confident we're going to have a complete transfer of our solution. But again, the con is that if we want to thinking about limiting contamination, we're going to have to change pipette tips. So again, that's going to require us to use a lot of pipette tips. So we're going to be very clean in order to minimize contamination, but we're not going to be very green. So one of the sort of workarounds I want to kind of talk about right now is something that we're going to see in a couple labs, but I just kind of want to highlight what it is. The first thing is to think about if you have a bunch of materials that you want to add together, if you put water in first, whatever goes in next, you probably can go into that same vessel again, because all you're going to have is what's in your pipette tip and then water in your Eppendorf tube. So you probably can go in and out and not worry about contamination because it was only water, and most of our solutions are water-based to begin with. The second thing that I want to highlight is creating what we call a batch buffer. This is a really important thing if you're doing multiple reactions that are essentially doing the same thing. The idea is that you make a batch of whatever common between them. And that way, when you add that to the solution, you're likely to have two important things happen. I usually quiz people on this. We kind of brainstorm through it, but I'm just going to tell you the answers. Reasons for making a batch buffer, two things. The first is you make sure you don't forget something. Okay. The second thing is you tend to have more homogeneity. So even if you remembered, let's say you had 5 reagents to go in each tube and you're doing 10 reactions, even though you might remember to put each one of those things in all 10 tubes, what if one of them was just a little bit less in terms of its amount than another? That could be problematic because maybe that's an important reagent that's going to be necessary to make sure that you get the right, results from your experiment. Maybe it's a concentration of a metal or something like that. So again, what you're going to do is you're going to make a batch. Let's say that 4 out of the 5 reagents are the same with all of those. So what you're going to do is make a batch that has those 4 ingredients in it, and then you're going to disperse that. So the main benefits of using a batch buffer, you save time, okay, that's a huge thing, but also it ensures you don't forget things, and it makes sure to, connected with that, you don't forget things so that everything has all of the same reagents, right? It has the same amounts. You put that in there. Usually give a cookie analogy here, right? When people are making a batch of cookies, they don't make one cookie at a time. They make a batch of buffer, and so then you spread that out to make all your cookies. Okay, so when you think about batch, think about making a batch of cookies. Anything that's the same within all of those cookies, you can put in together. All right, so you will have a sheet then that you can use to do what we call a workflow. So most of the labs, I have workflow sheets, which literally are your step-by-step directions with what you need to do. So for each of these, I want to go through these in fairly good detail beforehand so that you're sort of aware of what you need to do when you come into lab. All right, so big picture, 2 things you're going to be doing with pipetting. The first thing is you are going to weigh out a specific amount of water on the balance, okay? You're going to try this using the 3 different methods: shooting, touching, immersion. Okay, so you're going to find out which one is most accurate by seeing which volume corresponds to weight. And we usually go through kind of a little kind of a brainstorming session about why do we think that is. Well, the density of water is 1 gram per milliliter. So if we weigh the water, we're getting a direct measurement of the volume of water. Okay, this is how you calibrate pipettes, is you actually see when I have a measurement that I pull up in terms of liquid, do I get that same weight in mass of water? So that's what you're going to be doing. You're going to do each measurement 4 times. That will look for precision. Remember, precision is how close your measurements are to one another. Accuracy is how close is that weight in grams to what your pipetter is saying in microliters. Okay, or I should say micrograms or milligrams there. So in that case, we're going to be looking at precision and accuracy with this. So you're going to have 12 measurements because you're going to be doing 4 measurements times 3 different methods. So how this is going to work, you have a balance that's there. You're going to have a little weigh boat. When you're doing the touching or the shooting method, you're going to do that one first. You literally are going to tare your balance so that it says 0. You're going to pull up the volume that you're supposed to measure out, and then you're going to shoot it into the weigh boat. You're going to watch the weight go up, and you're going to record whatever weight it says. Then you're going to tare it, and you're going to do that 3 more times with the shooting method. Okay? Record that data. Now you're going to do the same thing, but you're going to do with the touching method. So again, you're going to tare your balance. You're going to have your weigh boat in there. And now what you're going to do, rather than shooting it through the air, you're going to touch your pipette tip to the side of that weigh boat, and then you're going to release the water. You're going to see how much goes in there. All right? Do that 4 times. 4 times is looking for precision. Then you're going to switch to the third method, which is immersion. Now you've already got water in your weigh boat. You're going to tare it so that it says 0. You're going to do the same thing, but this time you're going to put your pipette tip in the water. You're going to release the plunger. You're going to pull your pipette out before you release your thumb, and then you're going to see how much water you delivered by measuring the mass. Okay? Hopefully that should only take each person, maybe about 5-10 minutes to do, taking 12 measurements that you're going to record of water. The next thing that we're going to do, so again, this is that pipetting exercise. So hopefully this makes sense here. I'm going to highlight here. Each station is going to have a different pipetter and a different volume that you'll measure. So those volumes are here. You put that weigh boat on the balance, tare it to be 0. You're going to weigh additions of water by those 3 different methods. Repeat each for a total of 4 times. You're going to have 12 total measurements. You're going to re-tare it between measurements. And this is just, again, describing how those different methods work. There is a data table that you'll have in the handout. And again, this handout will be made digitally for you guys so that you can choose to print it out, use it digitally, whatever you want. But there'll be a table where you can put all this information in. The next thing that we're going to do as a group. One student is going to be sort of our data caller, if you will. That person is going to put 1,000 microliters into a clean weigh boat, and they're going to start a timer, and they're going to call out the weight every 10 seconds for 10 minutes. And I'm not going to say too much more here other than, Dr. Prenny, why am I going to write down the same number for 10 minutes? So let's think about, maybe it's not going to be the same number for 10 minutes, and let's think about what that actually might be showing us, okay? So there's a data table here where you can kind of write down all of that information. All right, so let's talk a little bit about spectroscopy now. Okay, spectroscopy basically is where you're going to have a light source. You're going to have some type of a monochromator, which is going to be splitting that white light, which is all wavelengths, into a specific wavelength of light. You're going to pass that wavelength through your sample. There's going to be a certain amount of light that comes through. The rest of the light gets absorbed by your sample. So there's absorbance and transmittance. There's going to be a detector that detects the amount of light that comes through. And at the end of the day, we're going to see something that looks like this. This is what we call a wavelength scan. This first picture here is a wavelength scan. It plots the absorbance value as a function of wavelength. And what we see that there's going to be certain wavelengths where we reach a maximum absorbance. We call this lambda max. So that's the wavelength where we have the maximum absorption. That's important because if we're doing an experiment, let's say on this substance that has a wavelength scan that looks like this, we don't want to be using this wavelength to measure because that gives a very small signal. Okay? We want to be measuring where we're going to see the biggest signal. So if we don't know it ahead of time, the first thing we need to do is do a wavelength scan so that we can see what's the lambda max. Okay? So you guys will do that first with some of the samples that we have. Want to just highlight here, difference in some terms here. Make sure that you are using the absorbance term rather than absorbance. This is paper towels and diapers. They do absorbance. We are talking about absorbance. So make sure that you use the right spelling. So again, when we talk about range, we want to think about what sort of acceptable ranges for absorbance values. So I generally like to think about absorbance values going between 0.01 and about 2.0. So if you are within that range, you're probably good. If you have something greater than absorbance of 2.0, let's think about what that means. Greater than 2.0 means that so much of the light is being absorbed, there's very little getting through, so our signal is very, very weak. That's not ideal. Similarly, when we get down at the very, very low end of absorbance, that means there's so much light getting through that it's hard to tell the difference between the light we started with and then the light that comes through. So it's a very small signal in that way. So let's talk about how you'd fix this if you were outside that range. Okay, so we usually brainstorm this for a little bit. I'm just going to tell you guys the answers right now. If you are too concentrated, that's actually the easier thing to fix. You can often dilute your sample. Okay, one of the things that we'll talk about on the next slide, but we've got Beer's law, which is absorbance equals our extinction coefficient times the path length times the concentration. Don't worry about that epsilon and that B as much as understanding that absorbance and concentration are directly proportional. We increase the concentration, we increase the absorbance. So if we have too high of an absorbance, we can decrease the absorbance by decreasing the concentration, and we can do that by doing a dilution. Now we have to make sure we know how much we dilute it by. Otherwise, we're not going to exactly know, how much we'd scale down that absorbance factor by. So that's the easier part. You can dilute something if it's too concentrated. Well, what if you have a situation where it's too dilute? That tends to be more problematic. That often is a situation where you might be below detection limit. And that just might be what the situation is. And maybe you know something's there, but it's too small to really be effectively quantified. Not really a lot of good fixes for that. You can try to concentrate your sample, but usually sort of evaporating water or things like that are a lot less specific than doing a dilution in terms of being confident with the factor that you might be concentrating by. Okay, so that's a little introduction to sort of spectroscopy. We had Beer's law that we wrote out on the last slide, but again, Beer's law is really a linear relationship between the absorbance of a sample and its concentration. This epsilon is really a constant, so it's not anything we're going to spend a lot of time thinking about or worrying about at this point. And then B is the path length. We'll talk about this, and when you see the cuvettes that you'll use in lab, you'll see that these cuvettes have a path length of 1 centimeter, which is great because mathematically we don't even need to worry about it. I'll show you a little trick when we get into lab. The path length of 1 centimeter is if a cuvette is in a certain orientation. If you turn it 90 degrees, it actually takes it through a smaller window. And so it actually can do the effect of decreasing the absorbance because you're going to be decreasing the path length by half. So it goes from a 1 centimeter path length to a 0.5 centimeter path length, which should decrease your absorbance by half. So for example, if you're up getting close to the 2 range, just turn your cuvette 90 degrees and you'll be able to then see that absorbance value go down. So a couple of practical things as you're thinking about doing spectroscopy. The first thing that you often need to do is you need to tell the instrument, what do I want you to ignore? What do I want you to pretend is invisible? And we call this a blank. So anything that you want the spectrophotometer to ignore. And so there's 2 options for sort of blanking an instrument. The first is to create a blank. And so as an example, we're going to be making a solution that we take water and we add some dye to. So just to make sure that there's not anything funky going on with the water, what we're going to do is have our blank be just water. So we're going to create a blank, and we can put the blank in the instrument, and this instrument actually won't even operate unless you provided a blank. It's sort of like a fail-safe. So again, this is a requirement by the instrument that we're going to be using. So you actually need to put in a blank into the instrument, and then you can say blank, it'll do its reading, and then it'll be ready to read a sample. Another option is you can actually put a blank in, measure its absorbance, and then manually subtract it from all your other data. That tends to be a more antiquated way. Our instrument, we're going to use option 1. I kind of went through and talked about already sort of this concept of a UV scan. Every substance is going to have an absorbance maximum at a specific wavelength. We want to be doing all of our measurements for that sample at that wavelength because that will give us the biggest and best signal to noise ratio. So if you don't know it ahead of time, what you might need to do when you have a sample that you're going to use for spectroscopy is do a wavelength scan, look at the wavelength scan, and then determine lambda max from that. Determining lambda max is really easy, and our instrument will actually do it for you. You'll actually just move a little cursor to where it's at the highest point here, and it'll tell you what that wavelength is. That's how you find lambda max. So a little bit more on spectrophotometry, right? We're going to have protocols for any of the instruments that we'll use. So those will be available for you. I'll have you guys look at the directions as I actually do the experiment for you. What's really nice about this instrument is it actually has a USB port. So when we do kinetics later in the semester, you actually can put a jump drive in the back end of it, and it'll gather all the data for you. So you don't even need to write anything down. Here is what those little cuvettes look like. It's a little bit hard to see here, but this is the 1 centimeter path length going this direction. If I actually had light going in this direction, it's going through a shorter path length there. So here's the little sample holder where we put our little cuvette in, and I've got kind of a little notification here. See where that little arrow is right there? That little arrow is going to allow light to pass through in this direction, being the 1 centimeter path length. So as just a rule of thumb, I always try to make sure that that arrow is facing towards me. That way I always put the cuvette in the right direction. Because remember, if we turn it 90 degrees, we take the path length by half. A couple of comments here as we're thinking about this whole green versus clean thing again. Do you need to clean out your cuvettes between measurements? So one of the things that I'm going to have us do so we can actually be a little bit more green is if you start with your low concentration sample, you can actually just dump it out, and then you can put the higher concentration one in, because it's not likely that you've got some contamination that's in there from the first one that's going to add some colored molecules to your second sample. So in general, you can probably start with low concentration, move up to high, and not worry about cleaning out your samples. This also assumes that you don't want to save your sample after you've done something with it. So our samples, we're going to be making 10 milliliters of a colored solution and just taking a small bit of it to analyze in our spectrophotometer. So in that case, we're fine dumping out whatever we used just for that sort of little assessment piece and then putting the next piece in. But sometimes you might be needing to take the measurement of a sample and it's like all your sample that's there. So if that's the case, yeah, you do need to make sure that your cuvette's clean when you put it in. And then again, when you take your stuff out, you don't want to be putting something else in if that something else is something you need to be saved. So again, that hopefully addresses this idea of, do we need to clean things out between measurements, and if we want to think about sort of ordering the measuring of samples that we have. All right, nuts and bolts, what's the workflow of what we're going to do here? All right, big picture, what you're doing with this spectrophotometry station is you are going to be making a series of colored solutions. Okay, they're going to go from a very faint blue to a very intense blue depending on the amount of dye that you put in there. Okay, so each person is going to be making one solution, and then what you're going to do is you're going to take some of that solution out and you're going to give it to me in a cuvette, and I will tell you what the data is from that. So with 5 people, we'll have 5 data points. If there's only 4 people in the group, I'll probably do the 5th one, because we're going to have 4 total groups that will be going, an A and a B group from 11 o'clock and an A and a B group from 2 o'clock. At the end, I will compile everybody's data together so that when you do your post-lab analysis, you'll actually have data from everyone. So it's kind of a quick way to get the massive amount of data that we want in a shorter amount of time. So you guys are each only going to be making one sample of all that we're going to need. So again, what are we going to do? Just the nuts and bolts. You're going to use a serological pipette. So again, I'm going to demonstrate how to do this when we're there. We have basically, remember in Gen Chem where you used to have those rubber bulbs that you'd need to use on a pipetter, and you'd have to like suck the stuff up and get the bulb off and then put your thumb on there and kind of roll it around? Those days are long gone. We actually have, it's a little handheld device that provides suction or pressure to either draw up or push out liquid. So we're still going to use those same pipetters, but now we have essentially an automatic bulb that will draw in or put out air to do that same process. So you guys are going to learn how to use that. That's called a glass master. And basically you're going to put 10 milliliters of distilled water in a test tube. So each person will have one test tube that we'll make. Depending on what station you're at, you're going to use a different amount of a dye solution that we have. You'll cover your test tube your test tube with a little piece of parafilm. You'll invert it to mix it, and then you're going to take 1 milliliter of that out and put it in a cuvette for me. I'm going to then go ahead and demonstrate how to use a spectrophotometer. I'll sort of walk through the details of it. I'll obtain some readings that will then collect together. You guys will have this data table that you'll put them down. Again, we're going to have actually 4 sets of samples that we'll have because we're going to have 4 groups. And then we're also going to do an unknown. So I'm going to provide you some data for an unknown sample. And then part of your post-lab is you're going to have to tell me how much dye you think was in that unknown. So we'll talk a little bit more about that in lab. I don't want to get too much into the weeds with post-lab. But then I'm also going to give you some wavelength scans. So this will make sense when we're there, but it's not anything you need to come to lab knowing how to do. What you're going to need to know to come to lab knowing how to do is essentially you're just going to have a test tube. You're going to fill it with 10 milliliters of water, and you're going to put a specific amount of dye that's in there, depending on where you're sitting. Once you get that, you're going to put a milliliter in a cuvette. And don't worry, I will tell you all of this again, but I'd like you to have heard it once already. And then we'll analyze those samples in the spectrophotometer. So that's our spectroscopy station. Our last station is on buffers. Okay, so this part is actually going to be done after lab. It's a calculation part. Usually we do the calculation first and have people sort of ballpark what they think the pH is going to be based on some calculations. But again, in order to front load us and have us use our time in lab well, what we're going to do is we're going to make a solution. So again, this is one of those key skills. We're going to talk about the different pieces of glassware, but what we're going to do here is use a 100 milliliter volumetric flask. So when we have our 100 milliliter volumetric flask, we're going to add 10 milliliters, in this case, of sodium acetate, which is our weak base, and then 5 milliliters of acetic acid, which is our weak acid. So I should say it's a weak acid and its conjugate base. We're making a buffer. And then we're going to add water quantity sufficient to 100 milliliters. So that's that language that we learned about in terms of making solutions. So I want you guys to know how to make solutions. If you're told to make a solution by mixing 2 things together and make 100 milliliters of solution, and then those things don't add up to 100, the balance needs to come from water. You're diluting those samples together. So we're going to make that. You're going to learn how to use a volumetric flask and make a solution. Everybody's going to do that. And then what's going to happen is I'm going to demonstrate how to standardize a pH meter, and then we will read the pH of each of your solutions. So again, you'll take a little bit of your solution out, you'll put it in a beaker, you'll give it to me, and then I will go ahead and read the pH for you. You guys will then do calculations for what you think the pH should be, and then if it's not what it should be, you're going to hypothesize maybe why. And part of a skill that I want you guys to learn in this lab is learning how to accurately sort of troubleshoot, not just say, oh, experimental error, the pipette was off, things like that. No, if your pH was low, what did that mean? Can you rationalize it based on something that you can think about experimentally in lab? We'll talk about that a little bit in lab. We should have time to do that in this 30-minute station, but just kind of wanted to kind of set you up for that. So there's going to be a bunch of questions again that you've been answering along here. That is going to be your pre-lab. So that's going to be how we sort of give you credit for doing your pre-lab and making sure that you're coming to class prepared. Can't wait to see you for our first wet lab.